This slide depicts the Karplus curve, proposed by Martin Karplus several decades ago, to explain the dependence on the magnitude of coupling constants with dihedral angles, or three-bond angles. The three-bond coupling constant is labeled as superscript 3, italicized capital J. For the Karplus curve, the coupling constant approaches 0 Hertz, just under a 90-degree dihedral angle. It reaches a maximum for anti-periplanar arrangement of hydrogens at 180-degree dihedral angles, and reaches a local maximum, slightly lower maximum, when the hydrogens are eclipsed with a syn-periplanar dihedral angle at 0 degrees. In many compounds, there are vibrations, there are rotations, and so the observed coupling constant is actually a weighted average of conformers, often at approximately 7 Hertz. But in the presence of a ring, or if there are some other steric factors that favor one conformation over another, especially a conformation where the hydrogens are fixed at 180 degrees, such as transhydrogens in an alkene, the coupling constant will be considerably greater. It is also known that heteroatom substituents on one or both of the carbons bearing hydrogens will diminish the magnitude of the coupling constant, usually by a couple of Hertz. There is also a Karplus curve for two-bond couplings, or geminal couplings. Two hydrogens on the same carbon of an alkene that are chemically non-equivalent will couple with each other, but the coupling constant is often so small, 1 or 2 Hertz, that it may be visualized as simply some broadening for each resonance. On the other hand, for sp3 hybridized methylene groups, where the hydrogens are chemically non-equivalent, the coupling constants can be quite large in the range of 14 to 17 Hertz. Table 3.6 from the textbook gives some general observed coupling constants in cyclohexanes. In my experience, the three-bond couplings for axial-axial hydrogens are often on the high end of this range, 12 to 14 Hertz. On the other hand, the equatorial coupling constants often have a dihedral angle slightly greater than 60 degrees, and the coupling constant can be very small, 1 or 2 Hertz, whereas the axial equatorial dihedral angle is often a little bit less than 60 degrees, and that coupling constant may be a little higher, on the order of 3 or 4 Hertz. In some actual proton NMR spectra, this is a proton NMR for THC, which is the psychoactive component of the cannabis plant. Specifically, this is the transfused diastereomer. For the alkene hydrogen, we see a little bit of broadening, suggesting a very small coupling constant, maybe 1 or 2 Hertz. What is most interesting is hydrogen labeled E. This is at about 3.2 parts per million in chloroform, and it is a doublet with a relatively large 11 Hertz coupling constant. You can see that the doublet is a little bit broad. That suggests that may be the 1 or 2 Hertz coupling with the alkene hydrogen A. The methyl groups are also labeled, and in particular for the gym dimethyl groups. In a two-dimensional structure, these methyl groups may look very similar, but in fact, axial hydrogens and axial methyl groups are often shielded relative to equatorial hydrogens and methyl groups. I'll show a three-dimensional model of the transfused THC. This is a model of transfused tetrahydrocannabinol. You can see the phenol, the cyclic ether, the alkene. And now I point out at the ring fusion, you can see the hydrogens are transdiaxial. Notice also the axial methyl group versus an equatorial methyl group. This is the NMR spectrum of the cis-fused diastereomer of THC. The hydrogens at the ring fusion are cis to each other. There are several differences in the spectra of the two diastereomers. One of them is that B is now slightly more shielded in the cis THC than it was in the trans THC. You may want to go back and take a look at that spectrum. Hydrogen E is now deshielded in the cis ring fusion relative to the trans diastereomer. It is a triplet with a medium-sized 5 Hertz coupling constant. For B, there is probably a 5 Hertz doublet, but the left line of the doublet overlaps with the resonance for A. And the geminal dimethyl groups now have chemical shifts that are much closer together. Here is a three-dimensional model of cis-THC. For cis-THC, let's look at the ring fusion. I'll point out that the dihedral angle is about 20 or 30 degrees. That's reflected in the smaller coupling constant. And then the methyl groups are also a little bit closer together, not quite as clear that one is axial and the other methyl group is equatorial. This is a two-dimensional picture showing the connectivity of atoms for another natural product. I've also provided the high-resolution mass spectrometry data that was used to determine molecular formula. Mass over charge of 275 from chemical ionization is from protonation, probably one of the oxygens. The fragment at mass over charge 243 corresponds to loss of a methoxy group. This is a deduction of 31 from 274. And the infrared spectrum indicates that there is a hydroxyl group in dilute solution where there is not much hydrogen bonding. This is a sharper band at about 3600 wave numbers. And then there are two carbonyls at 1733 and 1720 wave numbers. From coupling constants associated with specific frequencies for resonances, we can make stereochemical assignments for this structure. First of all, notice that the methyl group of the ester with the electron withdrawing carboxylate group is slightly deshielded relative to the alkyl ether. And then there is another methyl group, which is an aliphatic methyl group, and it is a doublet consistent with coupling with a methine at the adjacent carbon. Now it's time to either draw or make a three-dimensional model of this structure. I recommend starting at one end of the structure, perhaps at one of the terminal carbons of the structure, and build from there. From experience, I will start with the ring on the left, and I will actually start with the methyl group. For the attached methine, there is the 7 Hertz quartet coupling with the methyl group, and the remaining coupling, a doublet, is a large 10 Hertz coupling. So that suggests that these hydrogens will both be axial on a 6-membered ring. For the next methine, which we eventually determine is at a ring fusion, we account already for the 10 Hertz with the adjacent methine, and then there remains a large 10 Hertz coupling and a small 3 Hertz coupling. The 3 Hertz coupling correlates with this coupling for a deshielded hydrogen that's on a carbon attached to 2 electronegative oxygens. And so the 10 Hertz coupling corresponds to another 10 Hertz coupling, and there are just 2 candidates remaining. There's a resonance at 3 parts per million, and there's one at 2.59 parts per million. To sort out between these two, let's look at some of the other neighboring peaks. For the methylene with diastereotopic hydrogens, we see a very large coupling constant of 17 Hertz. That is for the geminal coupling. And then one of the hydrogens has only a 5 Hertz coupling, but that matches up with 5 Hertz coupling for the 3 parts per million, doublet of doublet of doublet of doublets. And then there is a 12 Hertz coupling for the other hydrogen of the methylene, and that couples with the only other 12 Hertz coupling that we see in the spectrum, also on the 3 part per million resonance. We have one 10 Hertz coupling remaining at this point. There's an adjacent peak with a 10 Hertz coupling. These 2 hydrogens may be both axial on adjacent hydrogens. And then we'll just make note of the last remaining resonance has an 8 Hertz coupling. That's fairly large, could also be another axial dihedral angle, but the magnitude of the coupling constant might be diminished by the 2 electronegative oxygens. Let's now try to draw the 3-dimensional structure. I will do this quickly, and admittedly, it is much easier to confirm once the structure has been determined by someone else. I'll draw a 6-membered ring in a chair-like conformation for the tetrahydropyran on the right, and the 2 carbons of the other ring at the trans ring fusion, as well as the trans diaxial hydrogens at that ring fusion. I'll add the other substituents on the pyran ring. Since the hydrogen at 2.59 has large coupling constant, that must be also in an axial position. Therefore, the ester is pseudoequatorial. And then at 5.45, 8 Hertz coupling suggests another axial hydrogen. That puts the methoxy group in an equatorial position. What then remains is the resonance at 5.88 part per million, the small coupling constant, and the de-shielded chemical shift relative to this chemical shift suggests that the hydrogen is not axial, but rather is equatorial. That puts the hydroxyl group in an axial position. For the rest of the structure, this methine with large coupling constants is probably also axial. That puts the methyl group equatorial, and then the oxygen of the lactone closing the ring. Since the lactone is somewhat conjugated between the oxygen and the carbon, this second ring, the ring on the left, is probably in a twist chair conformation. We can then draw in the hydrogens for the methylene, put in the carbonyl, and that completes our structure. For one last bit of evidence, they functionalized the hydroxyl group as a benzoate ester. I'll show that on the next slide. The authors reported chemical shifts for only a couple of hydrogens. The hydrogens that are colored in purple are now shielded relative to the hydroxyl compound. I'll redraw the three-dimensional structure. It's a little easier to draw it once I know what the entire picture will look like. And where the hydroxyl group was, I now add the benzoate. And this is consistent with the aromatic ring current shielding 2 of the axial hydrogens. Unfortunately, the authors did not publish the entire data set. I don't know how the other axial hydrogen on the top face is affected.